Hello everyone, welcome back to another video. We're going to be watching some more DSA stuff today. And we are going to be covering quicksort, doubly linked lists, maybe some trees. We'll stop at the 2 hour mark. So it looks like these are kind of long videos. So we might just actually cover another two sections and then pause there for today. So without further ado, let's get right into it. I'm going to first set up. So my Anki is set up, but I do need to navigate to it is Kata machine. Right? All right. Yep, perfect.
Actually to the end of the array list section. Actually, for real, this is it.
For real
We're
this
gonna do
time.
one last algorithm, and that's it. So hopefully we all feel pretty dang good about this. Remember, you may have forgotten, but I said we're gonna do two sorts, right?
Right.
We're gonna do bubble sort. No, we're doing it. We're doing it. And two, quicksort. Quicksort is a fantastic algorithm. It's shockingly simple, and at the same time, it's like shockingly brilliant how someone could come up with this. To me, it just blows my mind. I don't think I could come up with it by myself, but whoever did it, maybe the constraints of having a really slow CPU would have made me come up with this, but I just didn't have that problem, right?
Fair enough.
Born in the gigahertz days, right? Kind of makes you forget how great things are. There's actually an algorithm technique known as divide and conquer. So normally in algorithms book, often you'll see merge sort as the one they use, but this one we're going to use quicksort because I want it to be different. You can go read about someone else's merge sort. That way you have more breadth of things people will explain. So what is divide and conquer? Effectively, divide and conquering is to be able to split your input into 2 chunks, 3 chunks, 4 chunks, whatever the splitting is, and then be able to go over those smaller subsets and solve things faster. Then you could resplit it again, and resplit it again, and resplit it again. It becomes something in which progressively gets smaller and smaller until it gets to some sort of fundamental unit in which you can solve really easily. So think about sorting. An array of one element is always sorted. So that would be like, say, the fundamental unit in merge sort is once you get down to that point, your array is sorted. Now we need to just do the undo function, which involves merging, hence the name, merge sort. All right. There are a bunch of different algorithm strategies. I didn't technically really name any of the algorithm strategies as we go. There's greedy. So linear search is a greedy search. We go until we find the first one. We're done. There's also dynamic programming. Dynamic programming is one of those things that until you really get it, it's really, really hard. And for whatever reason, almost every single company asks you the same. If you had a stock chart, what is the best day to invest in? Which is just a dynamic programming problem. Oh, it's very annoying. All right, so first we're going to go over quicksort algorithm. It really is a super fun algorithm. Yeah, by far one of my most favorite ones. I think get the program. I have a fun story about it, which I'll go over here in a little bit. But for now, let's just talk quicksort. All right. Do you like that? Do you like that? We can even use quicksort.
Quicksort.
All right. So quicksort works in such a way that it divides and it conquers.
Okay.
So let's just pretend that we pick some element out of the array. Doesn't really matter what the element is. We're just going to call it P. And the reason why I call it P is often this element is referred to as the pivot. And so let's just say, for our sake, we'll just make it simple. We pick the last item in the array. We pick the last item, and then what we do is we have an index that hangs out over here, and we walk our entire array. So then we have a second one that's going to walk our entire array. Any element that is less than or equal to our pivot will be put in the first little runner's position, right? So we have that first pointer that just starts at the beginning, a second one that just walks the array. Every time we find one that's smaller than our pivot,
fast as fuck, boy.
In that first position, increment our first runner. So we're putting
still fast as fuck, boy. Come get some.
Equal to our pivot on one side of the array, then our pivot, then all the ones that are bigger than it on the other side. So starting to kind of look like sort. You can already see a sorted item in here. So eventually what we should see is that our first pivot should be somewhere in the middle-ish, right? Who knows where it's going to be. And everything on this side is going to be less than or equal to. Everything on this side should be greater than. This is referred to as a weak sort at this point. You'll see other data structures tomorrow that actually take advantage of an idea
tomorrow
to make super fast operations.
Oops.
And so it's actually pretty cool. And then at this point, we need to split our problem in twain. Yes, twain. We are going to take the positions betwixt the pivot
oh my god
and the ending,
betwixt
and betwixt the other side of the pivot and the beginning. And we repeat the process again. Pick another pivot. We'll call this one pivot 1. Eventually, pivot 1 will be somewhere, say, in the middle.
Sure.
And pivot 2 will be somewhere, say, in the middle. And then we'll split it again, where we don't include the pivot, but we include everything around the pivot. And we just keep on doing this operation until we get to a specific case, of course. You can imagine an element of nothing, or an array of nothing, or an array of, say, a single item,
right,
always sorted. Once we get to that point, we're completely sorted. Make sense? Hopefully it does.
Sort yourself out, dude.
And what can we say about, say, P1? Everything on this side is greater than P1, but we can also say something else. Everything right here, it's still smaller than or equal to our parent pivot.
Yeah.
So it becomes progressively more sorted at this point. Progressively more sorted at this point. So let's kind of think of it in a different sense. Let's draw it in a different way. How I'm going to draw it is in a tree. This really would help visualize also the execution of it all. And from here on out, I'll probably be referring to this thing as the low, one side, right? And the high, the other side. Should kind of be reminiscent of binary search. But there is going to be one difference. As I program and as I do things, I'm going to have my low be inclusive, and I'm going to have my high be inclusive. Very unusual. Most algorithms don't do this. I find that this one's much easier to be inclusive instead of exclusive. You'll see why as we get there. Just remove some plus ones that can make things tricksy. All right. That's Gollum for tricky. All right. So let's just say we have an array that is 32 big. And so we have from 0 to 31. And we pick a pivot, and it ends up being the middle element, which is going to be 16. That means when we do it again, we're going to have two subarrays, right? And that subarray is going to be from 0 to 15. We don't include 16 because we've already sorted that singular item.
Right.
And it's going to be from 17 to 31. Does that make sense? Yeah. All right. Then, again, we get the middle element. We can do it on both sides. What is the middle element here? 24? That seems to make sense. I'll just keep on going down this one side because I don't think you need to see both sides being created. Just repeat it. That means we're going to have to do two more. We're going to have 1 through 7. And we're going to have 9 through 15, right? Just changing up my symbols there. I used a comma for whatever reason. All right. Awesome. Again, we pick a pivot. It's in the center. We do it again. So what is the center of this one? Is it 4? I think it's 4.
Yes.
And this one, we're going to have the center of here of 12, right? So that means we're going to have 9 through 11 and 13 through 15. Awesome. Oh, man, I'm running out of space, aren't I?
Indeed.
Then we're going to have 5 through 7.
You never give yourself enough spaces when trying to build a tree. It never happens.
Your brain just makes new decisions as time goes on. And eventually we get down to the point where if we pick another pivot, we'll have 2, then we'll have 1, 1, 3, 3, 4, 4, whoopsies, 4, 4, 5, 5, 6, 7, 7.
I need to move that. That stinks.
9, 9, 10, 11, 11, 13, 13, 14, 15, 15. See how that kind of broke down? We slowly kept dividing the array in half and half and half.
Yep.
And eventually, when we're at this bottom part, all of those pieces are sorted at this point. We're done sorting. We have them all. And so, again, what we're seeing here is that we're seeing a way that we break the problem down more and more to the point where everything eventually becomes sorted. Obviously, everything this direction is less than or equal to, which this direction is less than or equal to, less than or equal to. And so eventually, then it becomes simply sorted. Then this whole thing is 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 sorted. Right? It walks back up and it does the whole sorting, and it can do it all in place, which is really impressive, instead of having to create a bunch of temporary structures for holding values. And I think that that is a very, kind of key point to this whole quicksort business. Again, this is why we did recursion before we did this step. It's because you can see right away we have this branching factor within how we're solving. The branching factor is, of course, 2. We have 2 branches every single time we execute quicksort. And something else you should probably observe right away, which is based on this little thing that I've drawn right here, we had to go over all of the input once, right?
Yeah.
Then, when we were at this level, we had to go over still all of the input, right? Save this one little pivot. Then we went over all of the input again, save this one little, the couple pivots that we've now created. We keep having to scan the entire input every single time until we get down to the very bottometh level, which means that we have to do n operations all the way down to when n equals 1, which, of course, is our beautiful equation of n equals 2k equals 1. Remember that? Do we all remember what that equals? Log n. There we go, which means our running time for doing this is going to be log n, or n log n. We scan n times, we do an n log of n, hold on, we do a log n amount of n's. Yeah, there we go. And I knew it eventually would come out of me eventually. It'd get there. But is that true? Is that true?
I don't know. Is it? You tell me.
Does anyone see any problems with how I kind of described this?
I think, what if you don't get in the middle?
Boom! That is exactly it. Quicksort doesn't always sort quickly. I know.
Right.
It's a very deceiving name. You never know what you're going to get out of this one. So can anyone think of a condition based on how I've described the algorithm which will actually produce the worst possible answer?
Like it ends on the side.
I did it.
It ends on
making it a little bit easier.
If you start at the beginning.
Yeah, if we were right there. Yeah, so oh my God, perfect. It's ridiculous. A reverse sorted array, right? If you are handed an array that goes 10, 9, 8, blah, 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 down to 1,
Yeah.
and I pick this number, what happens to our pivot? Well, our pivot looks something like this. 1, because it's just hanging out there by itself. Because remember, we put everything on this side of the array that is smaller or equal to it, and then we put it at the pivot point.
Right.
Oh, that kind of sucks, because we now are sorting n minus 1, right? Then we do it again, which is now 2. Goes over, goes over, goes over. It goes all the way up for n amount of scans, n minus 1 amount of scans, n minus 2 amount of scans. What's the running time of this one again? N squared. That is right, because it follows the old third grader formula of n times n plus 1 over 2. Fantastic. We have now just done that, which of course breaks down into the classic n squared over 2 plus n over 2, which drop all the constants and lower order stuff, and all we get left is that right there.
Right.
So that's what happens. So quick sort is not just simply n log n.
This is a good refresher from last.
N squared, which totally sucks. That's not what you want. And so there are some strategies. One of the big strategies is always pick the middle element. If it's reverse sorted, you should get perfect bisecting. If it's sorted, you should get 0 swaps. If it isn't, if it's just completely random, you'll have a random chance of being somewhere nearest the middle, right? I think over time, you'll probably fall within a certain, certain middle region more often than the fringes. I'm pretty sure everything usually always ends up being a normally distributed function, but you'll get somewhere
the
in
worst
this
case
n log n
scenario
squared range. So this
for
is why
a
quick
quick
sort is kind of
sorting
tricky.
algorithm?
If you read about merge sort and you see it, it always does n log n
How
time,
do you avoid
but
it?
the constant in front of merge sort is rather large because it has to do this whole array
A
copying,
reverse
kind of
sorted
moving things around
algorithm.
type item that isn't necessarily the most conducive
Select
to high-speed, low-memory algorithms.
a pivot
And
point
so quicksort is often the one that is
in
reached
the
for and
middle
does really, really
of
well,
the array.
but it can have poor performance if you just hit all the right conditions. Again, the chances of you hitting all the right conditions all the way through to get n squared is exceptionally low, I would assume.
Exceptionally low.
It's somewhere
But
between
we'll see.
n log n best case, n squared worst case, somewhere in
What
between.
is
So
the
fun
quick
one, huh? It's kind of interesting. It's one that you
sorting
can't really fit into a runtime, which I think just makes
algorithms
it more fun in general to learn about.
runtime at best and
And
at
I
worst?
think that's all we have to do with it, except other than the fact that I'm going to tell you
At
this really cool
best.
story. All right, so this real cool story is that I was on
We'll
a
stop
team.
here for a moment and we'll say at best it's going to be O of n log n. N log n. And at worst, it is O of n squared. Cool. So now we get to hear story time.
Team that was the first team to be a non-MIT student team to make it to MIT's finalist in MIT Battlecode. So Battlecode is where you program these little computer robots. They're like simulation robots, and they have to battle it out. And you have to do all this different type of fighting. There's macro, it's like imagine StarCraft, right? It's like StarCraft, but for people that aren't smart. And so it's like really, really simple, and there's very few conditions. There's no races. It's just like people in a base often. And there's every single year, it's a little bit different. Sometimes there are races, sometimes there aren't, blah, blah, blah. It's pretty cool. And when we were doing this, I had this thing where if a certain resource was between us and our opponent, then I'd want to capture that and turn it into a turret, right? So if they tried to come near us, we'd be able to shoot them really easily, super, super easy. They couldn't get us. It was a way to just dominate them, right? And so I thought, okay, this is what we're going to do. I could take all of these different resources that are on the map, and I can just simply sort it and find which ones we need to do certain different things with. It should be really, really simple, right? Well, of course, the constraint with MIT Battlecode is that you only get 10,000 bytecode operations. This is in Java. Everyone loves Java. Which means
Everyone
you actually get very
loves
few
Java.
things you can do any one turn per person. So I couldn't quicksort it. Within like 5 elements, the guy would come out of the base and then just sit there for like 20 frames and just be dead in the water. And then as the base got more of them, sometimes they would just stop, and then our whole thing would stop, and then we'd just die. We're like, what is going on here? And it came down to the sorting algorithm. You couldn't simply sort because you'd run out of time. You'd run out of computational that's available per turn. And so what I realized is that if you look at this thing, what you're going to see here is that this is just a tree, right? This is just a tree filled with states. And so if you really think about it, you don't have to do this recursively. You just simply need to know where you start, where you end, process that thing, and it may produce 2 children. If it produces 2 children, add it to a stack. And then you can actually get the exact same thing. So that's all I did was every single turn I'd go, hey, how many do I have left? Which there was a function to say how much computation you had left. And if I was like, hey, if it's below 1,000, then don't do any more sorting. Go do your other thing so you can like move around. You can see if there's bad guys near. You can do other operations without running out of space. And so it became this kind of like simple way to avoid running out of space. So these things do become useful. Obviously, that is an obvious case in which it's so specific you'll probably never run into it. But nonetheless, it is something to always, that's kind of fun to think about, that you can use these algorithms in really unique ways that actually become super useful. And I'm sure that taught me something that I've used throughout my life. I want to end on a positive note somewhere, right? It was great. All right, we got 13th, which means we lost in the finals right away. All right, so we went over the running time somewhere of n log n all the way up to n squared, depending, right? And of course, next we're going to implement quicksort. Hey, did you know that I teach a course on Vim? This sweet editor that I'm using that's super fast and super cool and goes really, really, really fast and all these great things. Yes. So if you're ever curious, I do a developer productivity, which allows for sweet this and Vim usage and all the great stuff. Fantastic. Okay. Anyways, back to it. You have to sell your own course, it's just a part of things. All right. So let's do quicksort. So this is the test for quicksort. I have a debugger here because obviously I've gotten it wrong multiple times in my life. So this is the array we're going to sort, and hopefully we can sort this. So let's just jump to it.
Sure.
And now it's the sorting time. So we get an array, and we're expected to sort.
Yeah.
So there's two functions that we really need to think about. If we replay what I talked about, there was this whole running these two things side, right?
Mm-hmm.
But there's also this whole pivoting side.
Right.
So often when you see quicksort, it's split into two functions. There is something referred to as the partition. I think that's how you spell it, which actually produces the pivot index and moves the items that are less than or equal to on one side and the items that are greater to on the other side. Then the second thing is your actual quicksort, which does the quick sorting, which calls partition, gets the pivot, then recalls quicksort, does the recursive step and the base case step, and does all the kind of the bookkeeping. So we usually break it up into two different functions. So let's start here, and let's just create a function we're going to call quicksort, right?
Quicksort.
So I'm just going to call it QS, quicksort, make it easy. Pass in the array.
This is for pivot.
So the high, remember, what did I say specifically about the high? I think I said it right on the screen too. Did I say it on the screen? Yes, I did. Right there. It's inclusive. A very unusual thing you do in most algorithms. You don't do that. So let's do r.length minus 1, minus a smiley face.
Okay, so what just happened here? He started writing. I want to go back to before he started writing.
Quicksort does the recursive step and the base case step and does all the kind of the bookkeeping. So we usually break it up into two different functions. So let's start here, and let's just create a function we're going to call quicksort, right? So I'm just going to call it QS, quicksort, make it easy. Pass in the array, and then we need to pass in the low.
Oh, he's calling it that. Okay, so he's
high,
just...
remember, what did I say specifically about the high? I think I said it right on the screen too.
It's inclusive.
Did I say it on the screen? Yes, I did. Right there. It's inclusive. A very unusual thing you do in most algorithms. You don't do that. So let's do r.length minus 1, minus a smiley face, minus 1. There we go. So now we just need to program two functions. The quicksort function, again, the recursion function, and then the partition function, how we get the index. So just to make TypeScript not give me a bunch of errors, let's go quicksort, r, number array, low, number, high, number. And what do we need to return out? Well, if we really wanted to, we could just return back out the array to make it super simple. We don't have to do that. You can do that. This one doesn't actually need the array right here, so we don't need to do that.
Okay.
Void. Awesome. So we have that one done, and then we need one more. We need the function partition, right? Partition right here, which is going to take in the array, the low, and the high. Because remember, this thing needs to be able to run on all these little spots in here, right? It needs to be able to run, on 1 through 7. So we need to be able to give it, hey, you're running from low, 1, high, 7, right? We have to be able to do all these things. So we have that right here, and it needs to return back out. What is the pivot index?
Sure.
Where did we end up splitting the array to? Where did we weakly sort this array? Awesome. So which one do we want to start with? Should we start with quicksort, or should we start with the partition? I'll let you guys decide.
Partition.
I love that. Someone had an opinion. All right, so let's start with the partition. So the partition shouldn't be too hard. We'll just do the easy way, which is I'm going to create a pivot, which is going to be simply the array at the high position. I know this could cause that whole sorting, reverse sorting, super duper issue, but let's just have an easy time with this. We don't need to do anything super fancy. Then at this point, I'm going to create an index. This is where, so most books will actually create it at -1. You'll see why they do it in a specific way. You don't have to do it this way. You'll just see in most pseudocode. I'm pretty sure if I went to Wikipedia right now, it would actually say that. Start at -1. So at this point, we need to walk from the low to the high, but not including the high, because the high is the pivot. So we just have to now do a weak sort on this subarray. So let's do the weak sort now. So for let I equals low, I has to be less than high, plus I. Now, what are we comparing it to? Remember, each element needs to be compared to the pivot, not like I plus 1, not something adjacent to the pivot. So if array I is less than or equal to the pivot, we now need to put that value into the first slot or the second slot or the third slot or however many slots we need to put it into to make this into a weakly sorted array. So we'll go like this. Const temp equals array I. Oh, forgot this. So in the most pseudocode, you'll find that they first increment the index at this point. That is now, we're now into the 0th position. We went from -1 to the 0th position, which I've also done something wrong here. We got to go to low -1, right? Because we have to be able to put it into, where is this? We have to be able to also, we need to be able to put stuff into the 9th position or into the, whatever position. Remember, because we're doing these little subsorts on these different spots within the array. Always forget to do that. That's one of the ones that got me multiple times. That's why that debugger message was there. Forgot to put or take advantage of using low. So low -1. So right now we're off of it. The moment we find something we need to swap, we move it into the first position. Now we do the flop. We're going to go array I is now going to need to be swapped with array index, or array I equals array index equals, what is it? Temp? There we go. Swapping. Swapping, I don't know why it's always so hard. I always mess it up. It's just the worst. So there we go. It's as simple as that. We've now found everything and moved it over into the beginning of the array that is less than our pivot. But we have one problem left. What is the one problem left?
We need to return a number. We need to return the pivot.
Let me tell you. Let's see if we can do this. Here. I'll do this. So I really want this one to sink in. I feel like Quicksort's just such a great algorithm. I just really want to make sure that people really get this one, which is, let's just say we had an array of 1,
well, we're gonna
7,
have to do this again.
6. I didn't plan on doing this, so hopefully this all works out swell. And let's go with 5. All right, fantastic. Let's go with 8 on this side. Perfect. This is going to be a pretty poor sort, but we're going to do it. So we pick 5 as our pivot.
Yeah.
And we start off with index that's here, off the thing, right? So we first check here. Is this less than 5? No, it's not. Though you are a crooked 8, it's not less than 5. Is this less than 5? No, it's not. Is this less than 5? No, it's not. Is this less than 5? It is less than 5. So let's move our index to right here, now pointing at this, and we are going to swap u for u. Awesome. And we're going to go up into this point, but not including the 5th one, because the 5th one, or that one, is that the 5th one? Oh, it also happens to be the 5th one, or the index 4, right there. So there we go. We've now flopped it. Everything's good. So our array looks like this: 4, 7, 6, 8, 5. 5 being our pivot.
Yeah.
So what's the last thing we have to do? We have to put our pivot where the pivot index is, right? So that way we hold true to the one rule, which is everything to the left of the pivot needs to be less than or equal to, and everything right of it needs to be greater than it. So we're going to have to do one last swap right here. So let's go back down here, and we go index plus plus, increment it once more. So if we found nothing less than us, we'd increment it into a position of 0, or low at this point. So we do that, and now we're going to go array high equals array index, and array index equals pivot. We already have the temporary specified right up there, right? So I didn't need to create the temporary variable in the swap. There we go. And the last thing we need to do, of course, is return the pivot index right here. Fantastic. We've done it. We've written the pivot form.
Index plus plus. So they went through and added to the index again. Okay, so if the current element is smaller than the pivot, increment first, assign a temporary variable to the current array index, and then reassign the current array index, and then give the temporary. The value of the current index is equal to array index, and what's in IDX is equal to low -1, which is the left all the way, the leftmost, just outside of the low. If it's smaller, we step 1. So now we're at low. Okay. And then anyways, if this doesn't work, we need to still step in, because this means that we've never stepped in. High has become the index. And then index has become the pivot. High, which is the end. And then index is the pivot. Oh, it's because... Wait, hold on a second. How does this work? Array index. What's array index? Low minus 1. So now, so let's say low was 0, minus 1. So array of 0 is equal to pivot.
The pivot algorithm.
We'll
Was that kind
figure
of
it
hard?
out.
Was that a lot to take in? Or, you know,
We'll figure it
hopefully
out.
these explanations, these things make it a little bit easier to kind of walk through and follow this, which is fantastic. All right, so let's go up to quicksort. So now we just need to do the quicksort side of things. So what's our base case? Well, when we get to the point where low and high meet, right? So that is a bad time. If low equals or is greater than or equal to high, I always put greater than, even though I don't think that can ever happen. It just makes me feel like I just catch all the possible conditions. I don't know why I do that. It just feels good. You know what I mean? So once this happens, we have now officially stopped needing to recurse. We've ended the line. So let's return.
Right.
Fantastic. If we don't hit that, we need to do 3 things. First, we need our pivot index, right? Whoopsies, which is going to be partition, and we need to pass in the array, the low, and the high, right? So this thing is going to do the weak sort.
So it's calling the
It's
next
gonna
thing.
set the pivot into the correct spot, then return the pivot's index. So now we need to just repeat this again, but we need to make sure we don't include the pivot index on our repeat. So quicksort array low to pivot index minus 1, right? Because remember, it's inclusive endings, not exclusive endings. So if we didn't have that right here, we'd have to do some math to make it all work out. We'd have to put +1s and -1s elsewhere, so we don't have to do that. Oh, we do have a question?
Why use 5 as a pivot?
Oh, in this case, all I did was pick the last element. So I wanted to make it identical to the algorithm that I did, which I just simply pick the last element. I didn't pick 5 as a good choice. I just picked it as the choice I programmed.
Oh, it's the last element.
All right. Then, of course, remember, we need to go to the pivot and beyond 1. I think I just quoted Buzz there for a second. And then we're going to go up to the high. So now notice what we did. We're going to repeat the quicksort on one side of the array, on the other side of the array, but we're not including the pivot. Does this make sense?
Yeah.
Everything's looking good? Now, I'm sure there's an over and under going right now, but do we feel like I've gotten this first try? Okay, we have just people are out there saying absolutely. All right, quicksort. So we're going to run this, and I get this one. Ah, look at that, we got it.
Okay,
There we
fantastic.
Go. We got that first
So it
try.
works. Let's see. Can we recreate this? We'll do quicksort here. Oh, this is the test. I don't want the test. I want quicksort here. So he said we're just going to be calling the quicksort function, right? So we call it quicksort, and what are we passing in? We're going to be passing in 3 things. The array, the number, the high, right? So the array, which is the number, we're going to be passing a number, the low, right? And then a high, which is array.length minus 1. I don't need to type this. I don't know what I'm doing here. Cool. So then what do? We need quicksort, which is a function. And it takes in 3 things. So it's going to take in an array, which is an array of numbers, a low, which is a number, and a high, which is also a number. And then we need a partition, right? So function partition, which also takes in an array, which is a number, a low, which is a number, and then a high, which is also a number. So this will help us figure out our pivot, right? So then we're going to say that if first things first, what do we need to do? We need to assign our pivot, right? So this is this. And so we need to assign our pivot. So it will say let pivot equal to array high, right? So we first start off with the pivot being the end. And then we're going to iterate over the array for let I is equal to 0, I is less than array.length, and then he says plus plus I. So if array I is less than pivot, right? If it's less than our pivot, what are we going to do? First, we are going to index plus plus. Okay, so that's what we need to do. We need to figure out what our index is. How did he go about doing this? Oh yes, he said let index is equal to low minus 1. Right, because we're starting on the left and our pivot is on the right. So if the array is less than the pivot, we first go into index plus plus, then we say const temp is equal to index array I, right? And then array index is equal to what? Array I. And then array I is equal to what? Temp. No. Array index is equal to array I is equal to what? So the pivot, if the current element is smaller than the pivot, what are we doing? We want to step in, and then we want to do a weak sort. So we want to take array I and replace it with the current element, and then replace the current element with array I. Index is 0, I is 0. No, index. I'll have to figure out what this is in a moment, but we'll do, then it is index plus plus again. And what did he do here? We'll have to cheat. I can't recall this part.
So low minus.
So pivot is array high. Yeah. Index is low minus 1. Const temp is equal to array I. Array I is equal to array index. And then array index is equal to temp. Okay. I had it backwards. It is equal to array index. And then array index is equal to temp. Okay. Right. Because at first I have to write it out. We have to first, okay.
Here we go. It's as simple.
And then once this is right.
There we go. Was that a lot?
And then the other part was that he said array high is equal to array index is equal to pivot. Now this is where I'm confused. Array high is equal to array index, and array index is equal to pivot. Oh, so this is him breaking it up. So this is him partitioning it then. So he says array high is equal to index, and then array index is equal to pivot. And then we need to return a number. Return index. Right? Array high is equal to index. And what's index in this case? So the new pivot is equal to the index, which is the new pivot. Array high is equal to index. And then array index is equal to pivot. Let's see if you can explain that one more time here.
Equals array once more. So if we found nothing less than us, we'd increment it into a position of 0 or low at this point.
Right.
So we do that, and now we're going to go array high equals array index, and array index equals pivot. We already have the temporary specified right up there, right? So I didn't need the.
We already have the temporary. Array high is equal to index. Yeah, so he has the temporary, which is pointed at the end. Right? And then he said the end is now the new index. So if index was if low was 0, and none of this passed, right? If low is 0, index is at -1. So we increment index, so now it is 0. And then we are saying array of high, which is like, let's say if the number is 5, or so in this case 4, array of 4 is equal to array of 0. Okay, so it is switching the last one, array of 4 is equal to array of 0 with the first one, and it is switching the first one with the last one. I see. And then it is returning the index. Okay. So now that we have our quick search, what do we need to do? This needs to return a number. Right? This doesn't need to return anything. So, what am I doing here? We'll do a quick search, and it's going to be from low. Oh, we need to give it the array, right? And it's going to be from 0 to low -1, right? And then we're also going to do a quick search from array low +1 to high, right? Because we're going to go before the pivot and then after the pivot. Oh, but not this. Sorry, not quick search. We're not going to call ourselves. So we're going to go, it's going to be partition. Is it partition? I think it's partition, right? Because then what's calling on this? Well, let's see. Does this work? npx jet, oh, not npm, but npx just quick. I don't think this is going to work. Yeah, one failed. Quick sort array dot to equal undefined. Receive expected -3. Expected 3 received +3. Okay. Well, let's see what this is to return here.
Variable in the swap. There we go. And the last thing we need to do, of course, is return the pivot index. Right here. Fantastic. We've done it. We've written the pivot out.
Okay. So.
Whoopsies.
All right. I knew that I was missing something. So it's if low is greater than or equal to high, return. And then he called pivot ID,
which is going to be partition, and we need to pass in the array, the low, and the high, right? So this thing is going to do the weak sort. It's going to.
Okay. This is QS, And this is QS. And then it's const pivot index is equal to, and this is where partition comes into play. And it's going to be the array low and high. And this is going to be, where is this going to go? 0 to pivot index, -1. Okay. Pivot index, VB, yank. Oh. Okay. Now let's see. Does this work? Also failed. Okay.
Set the pivot into the correct spot, then return the pivot's index. So now we need to just repeat this again. Excluded. I was pick. Second, excluding the pivot undergoing right now.
Array. Low. High. Now does this work? Also another failure. In line 0. Fatal, an error, line 0. What is this? Syntax error. Hello?
But do we feel like I've gotten this?
Number. If low is less than high, return const pivot index is equal to partition array low high, and then this, right? Array pivot index +1 high, okay, and then partition array number low number high number, and this is to return a number. So this is the only difference. So let's say const here. Index is low -1. If array I is less than or equal to pivot index ++, and then we'll do the swap. Otherwise, swap high is equal to index. Oh. I think this is array index, that's why. And then array index is equal to pivot, return index. And then this is sending the whole thing. Let's try this one more time. One failed. Where did it fail? Maximum call size stack exceeded. Why did it exceed? Call size stack array high. Low -1. Okay, well, let's take a look here and see it. Let's continue comparing.
First try.
Where did I mess up? I need more of the bottom of the code. Okay. So then if array is this, index ++, the temp is equal to array I is equal to array index, right? Yeah, array index is equal to temp. Sure. Index ++, array high is equal to array index. Index is equal to pivot, return index. Array 0, array.length -1. Okay, so what's the issue? Oh. This is low. Okay. Also still failed. Function partition. It's telling me it's failing at the partition. So it's in here. Low minus 1. Maximum quicksort. Maximum call stack size exceeded. One failed. Okay. So one more time. Let's compare our notes here. Const pivot is equal to the array high. Sure. Let index is equal to low minus 1. Also sure. But what is here? Function partition, array number, low number, high number. If array I is less than pivot, index plus plus, I is equal to low. Oh. Again. I don't know what I'm doing here. This is high plus plus I. Okay. Come on now. Nice. Okay. We'll do this one more time. What I'm gonna do is 7 down. We're gonna delete this, and we're gonna do the same thing here. Delete this and delete this. Okay. So let's recreate these functions because obviously it was not working out for me the first time. And let's see if we can do this again. So we're gonna have to pass the array. We're gonna have to pass 0, and it's going to be the array.length minus 1. Okay. So in here, what are we doing? This is our partition. First we need to do is we need to set our pivot to the final element. So it's going to be const pivot is equal to array of high, right? Then we need to figure out our index. So our index, let index, is going to be low minus 1, right? Because we're starting outside of the little component. So then we go over it, right? We'll say let I is equal to 0. Oh no, I is equal to low, I is less than high, and then plus plus I, right? So we're always comparing to the pivot, right? So if the array of I is less than the pivot, what do? We need to start doing our swap. So we'll say const temp is equal to array of I, and then we'll say array of I is equal to array of index. This is where we're doing our swap, and then we're gonna then fill in with array of index, which is going to be temp, right? Perfect. But we're missing something because we need to step into our index first, right? So what happens if it doesn't do any of this? Then we need to still step into our index plus plus, and we need to do the same thing. So our pivot is right there. So we're going to do our swap, which is array of high, yeah, is equal to array of index. And then array of index is equal to pivot. And we need to return a number, which is index. Right? So I think this looks a little bit better than it did before. So we're doing our swap here, and we're doing our swap here, which is array I, and this one is going to be array of high, and that's our temporary. Okay. So we're going to go 21 up, and we need to do a few things. First, we need to do our check, which is if low is greater than or equal to high, then what are we going to do? We just need to return. Okay. And then we need to also figure out our const, and it was something index, pivot index, which was us calling on partition with array, low, and high, right? And then we need to do the recursion, which was call our own function, and we're going to pass it the array. We're going to start from 0, and we're going to go to low minus 1, and then we're going to do the other side. So it's going to be from, nope. This is low to pivot index -1. And then this is going to be pivot index +1, and it's going to be high. Right? I think this should work. Nice. Okay. Second time's the charm. Very nice. Cool. We got it. Okay. So swap and then sort and basically recurse. So swap. This is how you do a quick sort. Okay. We'll say this. Implement a quick sort algorithm. Algorithm. Oh. So it's for this. Where is it happening? It's not. Yank plus. And then I can just paste in here. Yep. Cool. And I need to undo all of this. Yank. And before all of this, in here, paste this, and undo. This needs to be yank plus, and then here. Cool. Oh, undo. And there we go. So now we have this. We'll add this. Oh, I haven't been tagging them. Oh well. And we'll do this. Perfect. Let's keep watching. We'll go back to the questions.
All right. Then, of course, remember, we need to go to the pivot and beyond one. I think I just quoted other side of the array. First try.
Okay.
I get this one. Ah, look at that. We got it. There we go. So we got that first try. I just knew it. Complete confidence there for a second. So there we go. So that is all quicksort is. It's just a simple partitioning and repeat. This is a divide and conquer strategy. I find this one to be really, really awesome. Easy. It's much easier to program than merge sort. Merge sort, though often used, is very, very complicated in my book. So I like this one. Fantastic. And at that point, we did it. We're kind of done with lists. There's no more lists. We're going to be done. We're fully done. But technically, in a sense, lists are actually trees in some sense. You know, they're kind of like, they're very, very similar. So we're not really done. We're just kind of done, right? You're going to have a whole load of node-like opportunities coming up, and we're going to use a ton of recursion. So if you're not familiar, or if you felt like your recursion chops weren't quite up to snuff, you might want to take a moment. And so all programming eventually leads to trees. This is just a fact of life. The Falcor thing that I mentioned where I could have ruined all of Netflix, that's just a tree. Well, it's actually a forest, which is a series of trees that were also pointing to other trees. It was like a graph that was also a set of trees. It was very confusing. I can't quite tell what it was. It was a linked list and a tree and a graph all at the same time. Just depends on how you looked at it.
Just depends on how you looked at it. Well, chat, what I'm going to do is I am going to take a couple of minutes to run to the washroom in between sections. I'm just going to run a quick ad break, and then I will be right back. All right. So I'm back. I don't know. Are we back from ads? Well, I hope so, because what we're going to start doing now are we are going to be taking a look at doubly linked lists. And I think what I will be doing is I'll be stopping at doubly linked lists because in a similar fashion with the previous section, quicksort, we are going to try and implement the algorithm ourselves before moving on to other things for the evening.
Do have time to implement the linked list, so let's actually implement it. I'm going to adhere to this interface right here.
Can I turn this off?
And so we are going to actually do all of these. Some of them are a bit trickier. I actually did take the Java interface. I know no one likes Java anymore. It's not that cool to like Java. But
what?
Netflix uses a lot of Java, so
I like
cool
Java.
To like Java. That's what I told myself as we did this. So let's go over here. Let's go to our cog machine and let's open up linked list. If you wish to join in, we'll be doing a doubly linked list because they are doubly a singly. It's true. Mathematically checks out. No one can argue that.
True,
All
true,
right,
true, true,
so
true.
I actually nicely have everything kind of generated for you right here, I believe. I think maybe we may have written this at some point, but there we go. So here's the doubly linked list. Let's go through this and actually fill in all these operations.
Okay.
Just a side note, I did at one point implement this right here, this get. So I'm just going to remove that right now.
Boom.
So that way we implement it continuously. You know what I mean?
Yeah, yeah, yeah.
I just want to say Java is cool if you like money.
Java is cool if you like money. I like money. You like money too? We should be friends, you know? That is a shout out, of course, to everyone's favorite movie, Idiocracy. So there we go. So often whenever I'm doing a constructor, I like to explicitly set things. So let's do head undefined, even though we don't actually need to do this. So now if you remember when it comes to linked lists. All right, so to be able to do prepending, you may remember the operations. Let's jump back over to our diagram right here, and let's just kind of walk through just one more time.
Oh,
so
man.
Prepending does involve the head, in which we're going to need to be able to set in a new node at the head's position. Which
Right.
means, let's just call it G. And what we're going to want to do is we're going to want G to point to A first. Then we're going to want A to point to G. Then we're going to want the head to point to G. We're going to kind of want to do these in this operation. We don't want to lose A in our memory. We don't want to lose any of these things. We want to keep these operations in order as much as possible. So let's do that right now. So if we're going to prepend something, we can start off by first creating the node, right? The node, of course, is going to be a value item as node T.
Yeah.
Great. So now we have the node, and there's always is technically two conditionings to a prepend, or any of these, which is if there is no head, right, there's nothing here, we don't have anything, we can just set this as the head, right? We don't need to do anything fantastic. So this dot head equals node. Perfect. And before we do that, bookkeeping. See, I just forgot to. It's so easy to forget bookkeeping. This dot length
Plus.
right? Because we want to be able to know how many items are in this list. Okay, so if that's not the case, let's do those exact steps again. Remember, G points to A points to G, head points to G. We'll just do those three ones. So let's go like this. Node next points to our head, or in this case, it was A in that case, right? This dot head dot previous points to node. There we go. We've done the two directions. Now this dot head.
No dot next. So this is going from G to A. And then this dot head is at A. And we're saying this dot head dot previous is going back to G. Okay?
Head equals node.
And now then we are assigning the node.
There we go.
Okay.
We've now just officially prepended. There are ways to make some of these operations a bit easier, in which we're not going to do. Let's just remember that there's like this circular linked list that will make some of these operations a bit easier, but I'm just not going to worry too much about that. We'll just kind of do it the old-fashioned way, if you will. All right, so now we got to do insert at. Insert at is the exact same thing, except for now we're going to be doing it within the middle. We'll be doing the F operation right here, which is going to involve us pointing to the node we want to insert at. Then that node, then we got to make sure we point to the other node and do all that. So let's write this down. It's way too confusing. I realize I don't have hands for 4 points, and there's just no possible way I can actually get that done. So let's just write this thing out. So we'll rewrite it out as C.
Why? Like there's so much room underneath
and
this.
D. And these are two-way links. And we want to insert at C with F. Awesome. So F needs to point to C as the next. F needs to point to B as the previous. Then
Okay, so we're inserting
B's
before
previous
C.
needs to point to F, and B's next needs to point to F. There we go. We have broken the chain in that order. First, attach the new node. Second, break the old links. So long as you do it in that order, you're not going to goof anything up. It's pretty easy to tell when you've goofed something up, because as you program it, you'll realize, oh crap, this is not going to work out at all.
Right.
So as long as you keep that in your mind, it's pretty easy. But remember, this is insert at, which means we also need to traverse the list. So that does make it a bit harder. So we can go like this. Let cur equals this dot head. Well, technically, since we're building our own list, we can actually add a better interface. So if our index is greater than our length, we kind of have a problem, right? We can't really insert at that point, can we? So what would be a good move here? I would probably just throw an error, right? Oh no, right? You can't really do it at this point. I don't know what else to do, right? You're 2 nodes off. Should we create 2 dummy nodes with no values in them? No, we're probably going to screw that up. It's going to make our logic a lot more complex. Probably the right move to do.
Okay.
Well, there's actually something else that makes this a little bit interesting. What happens if our index is the length? Well, we're really just appending to the list, right?
Right.
So, I mean, we can technically just call append, right? Right? Yeah. Why not? What
Call
if
append.
the
Oh, okay,
index
so it's
is
calling
0?
append.
Well, we're just whoopsies, just prepending it, right? We've already written those two. All right, fantastic. We don't really have to concern ourselves with the edge bookkeeping. This is where a circular linked list would actually avoid this kind of conditioning, but we're not going to worry ourselves
Prepend.
with
Okay,
that.
we
There
haven't
go.
done
So now we have our
append yet.
and now we need to simply just walk, right? We need to just simply walk until we get to the index, and then at that point, we will have the node in which we need to replace. And there's things that we know that TypeScript doesn't know, so we'll have to do a bit of casting. So let I equal 0. I has to be less than index plus I. Current equals current.next. And of course, we also have to make sure current is like actually a thing as we get there, or else we're going to get null exceptions. Technically we won't, because we actually pre-prepared for this by using our length to do all that, but TypeScript knows nonetheless. So now that we've done that, we can go current equals current as node t. A little TypeScript magic right there, I guess. I'm not very good at TypeScript, so.
So what's happening here? Let current is equal to this dot head. Okay. And then he is traversing as long as there is current, and I is less than index, which was being passed. Insert at item and index. Okay, so we are being passed the index at insert at. Okay, so as long as it's less than the index, current is equal to current.next. Current is okay. So why are we just traversing without doing anything? Thank you for the hydrate, Haxel. What are we doing with that with the traverse? Okay. It's just traversing to the index. Okay.
For all the TypeScript ninjas out there that are probably laughing at how I'm doing this. There we go. So we now have current. It is a node. Now we need to insert our new one. Remember, the first thing we do is create our node and attach it to the positions we want it to be at. So node value item as node t. By the way, if you don't, I find this thing right here, this little plugin. Oh, I can't use my mouse. Sorry, I didn't realize I can't. This little one right up here that says insert. It's kind of nice. It's a little fun plugin. I think VS Code now just finally got this, which is you get context of where you're at. So if you're zoomed in, you can see your function signature. It's pretty nice. Highly recommend using it. It's a good time. So we can actually, I'm not going to put it inside the constructor or inside the node creation. I'll put it right here. But node next now needs to equal the current we're going to be inserting at, right? Because in our diagram, we actually put F before C, correct? We didn't put it after C. We put it before C.
Yeah.
So let's go nodes next equals current.
These are complex.
Previous equals current.prev, right? So we've now attached our new node. So now we need to break the previous links and point them correctly at our node. So we can say this, current.prev equals node. And then the last one, which is a bit more confusing, we have to go like this. If node previous, if that actually exists, which we do know it exists, but we'll just say if it doesn't, based on our little looping condition, or based on these little condition up here, it has to exist. But for TypeScript's sake, we'll go like this. We'll now say, hey, that one, we need to make sure also does the correct thing. I think we have to do it this way. Current, there we go. If the current previous is there, we need to do something with it. So current previous next equals current. See, do you see what we did there? So it's a little much.
Yeah.
Is currents previous's next needs to point to F instead.
Yeah.
Current previous next. We just have to kind of run that triangle there for a second. And so that is one way to do this. You can see that we have a lot of options. We have a lot of links. There's different ways we could have done. We can do this. We could have even created a previous node and just did it that way. But this seems to be a pretty straightforward one for me, I guess. Hopefully that all makes sense mostly. All right, so let's do append. Append is also pretty easy. Hold on, I guess, did I take care of bookkeeping? We didn't take care of bookkeeping. Classic, right? There we go. We've taken care of bookkeeping. We make sure that we increment the length as we walk. Oh, actually, we need to put that down here, don't we? Yeah, because append and prepend should do their own stuff. There we go. Sorry. Bookkeeping, always just the worst. Never liked it. All right, so appending is pretty much identical to prepending. We're going to go in here and we're going to go to the end. And as always, attach the node, update the links. Right, so if we did, let's do Z over here. We would, of course, attach to D. D would then attach to Z. And then the tail would be updated to point to Z. Correct?
Yep.
Now, one thing we don't have in here, I just realized, is I completely forgot to put in tail. So we do need to do something with tail at this point, correct? So let's go tail. We now added that thing in. We put in a tail right there. And that means our prepend also needs to have the same logic in it as well. My bad on that one. There we go. If there's nothing in it, we are an empty place. Then let's set everything to the first node that comes in. And we also do the same thing on prepend as well, or append. If it's the first one, we need to make sure our tail and our head both get set at the same time. All right, so we'll go back down to append. So what are the conditions? First, bookkeeping, 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 bookkeeping. I told you this one is like, it's really lengthy to implement, right? There's a lot of little conditions in linked list that is shocking because they're very easy to use.
Okay, so he has it split into 2 different videos. So we will do the first
so
3
now
then, and then we will also go
operations.
along time.
First, create the node, attach it to the tail.
Right.
Then tail to the node. There you go, right? Just kind of do the 2 ways. So let's go const node equals value item as node t. Most excellent. If there is no tail, well, same condition. This dot head equals this dot tail equals node. Return, right? It's the first item to be put into this list. Awesome, we got it. Everything's good. Else, we need to do something now. We need to take our tail and we need to point to it. So
right.
Node.previous equals this dot tail. We have now pointed to the tail. Now the tail needs to point to the node. This dot tail dot next needs to equal node. Now we need to update the tail to point to our newly added node. This dot tail equals node. Dot next needs to equal node. Now we need to update the tail to point to our newly added node. This dot tail equals node.
Okay. So let's see if we can recreate this. First, we need to do first a couple of things. So we have public. This dot length is equal to 0, and it's an int, right? What is happening here?
Have in here, I just realized tail right there, and that
Public length is equal to number, private head, which is going to also be a number, and then private tail, also a number. Now we need to create something here. We need to say const node t. What does that have? It's going to have a value, which is a number. It's going to have a head, which is a number, and a tail, which is also a number. No. Node t. Right? Because, okay. T. This is just t. Oh, it's not const, but type. Type. Okay, now this should work. So type, value, head, tail. Okay, so then we have private, and this is going to be this dot length is equal to 0. And this dot head, which is equal to this dot tail, which is equal to undefined. Right? So then now we need to prepend. So what does prepending mean? Prepending means we are adding to the beginning. So if we're adding, this is where we add G to. Okay, so then we need to create the node first. So const node is equal to value item as node t, right? So if no this dot head, right, then this dot head is equal to this dot tail, which is equal to node, right? I don't think it likes that, but I think it's the same thing. If no, this dot head is equal to node. If there isn't a head, then we need to make the head is equal to the node, and this dot tail is equal to node, right? First we need to do is make sure that the length goes up. So this dot length plus plus, our bookkeeping. And then I think it's just head. No.
Forgot to put in tail. So we do need the
He forgot to put in tail.
as well. My bad.
If no, this dot head is equal to this dot tail, which is this dot node, which is equal to node, and then return. So why does it not like that? Right? Why do you not like this? Anyways. So if it does exist, what do we need to do? First, we need to attach, then we need to reassign, right? So we say, first we are prepending, so node.next is equal to this dot head, right? Oh, this is next and previous. I see. 26 up. My error is here. I think this is next, and this is previous. I don't. They are. I think.
That on that one. Well, our index next. I'm just not going to worry too much about merging it with. We'll just kind of want to do these things. Now we have the node.
Yeah. So next and previous. And he still doesn't like it. This is when we are inserting at. Let's go over insert at. Yeah. No, we still need to go to our prepend. If no, this dot head is equal to this, return. No dot next, this dot head dot previous is okay. I don't know what it's not liking about this. No T is not assignable to type number. Oh. If I can read, then it will really be helpful. Yikers. Okay. So then what do? We go 17 up, and then we go no dot next is equal to this dot head. This dot head dot previous is equal to node, right? And then this dot head is equal to node, right? Okay. So now what? This prepends works properly. We need to do our bookkeeping for here. So same thing, we'll say const node. I hate this D button. It doesn't really work very well. Const node is equal to, so it's going to be value, and it's going to be item as node T. Okay. I don't think we need this. Maybe, we'll see. So if index is greater than what? Oh, idx is greater than the node. So how do I traverse to the index? How do I find the index? Item. So item T is the value. But how do I get to? So we need to find the index, and if the index is greater than the node, what did he do here?
Also need just throw. Let me know.
Oh, this dot length. Okay. Throw new error. Oh no. Cool. Then it is else if index is equal to 0. What are we doing if the index is 0? We just return. No. If the index is 0, which is the first element, so then what do we do? We don't need to traverse, right? So we then push this dot head dot previous. Oh, I see. It's because he is doing index dot length. He's making use of the other. It's going to be this dot append index, right? No, this dot append item. Okay, and then one last thing is else if index is equal to 0, then it is, again, this is where we do the beginning. So I think
We've already written those two.
okay, yeah, and we have to return. Okay, and so now we are traversing. So it's going to be let current is equal to this dot node. No, this dot head, right? And so we need to traverse, which is for let I is equal to 0, I is less than current. No, I is less than index, and then I plus I. We are just traversing. So we said current is equal to current dot next, right? So now that we are at the element, I will need to change the length though. When do I change the length? I think it's this dot length plus plus after traversing, right? After traversing, we add to the length, and now we start inserting. So to insert, what do we do? First, we need to insert, then move things, right? So so what are we inserting? We're inserting a node, right? So are we going to be inserting the node the same way that we did the last one? So we'll say const node is equal to value item as node t, and then so first we need to insert. So node.next is equal to current this dot head, right? Node.previous is equal to this dot tail, right? So now we have the node pointing to this head and it's pointing to the tail. And then what do? We said we needed to go from this dot previous dot next is equal to node. This dot previous dot next is equal to node. And this dot head is equal to node. Right? That's what it should be.
That person laughing after C, we right know it exists, but we'll just say I think we have to do it. CD needs to point node and just do it that way, but this seems to be a pretty straightforward one for me, I guess. Hopefully that all makes.
So my shit's different here. Const node is equal to value item as node t. Node dot next is equal to current. Well, would this work? I don't know. It doesn't seem like it. To current dot previous. And this is going to be current dot previous. This is going to be current dot head. And this is going to be, we need current is equal to current as node t. And why are we doing this? We're just making sure that we're reassigning it with the values, right?
Sense seems to be pretty straightforward. Could have used this. What we did there. Current. There you go.
Current dot previous is equal to node. If current dot previous node is equal to node dot next is equal to current. Node dot previous is equal to current dot previous. Current dot previous is equal to node. And then it says if current dot previous. So if there was a previous before, but if we set it as node, isn't there already a current dot previous?
Is there? We need to do something. CDC.
This is where we put the current dot previous dot next is equal to current, and this is because we were pointing towards the last one, and it's pointing back to here. Okay, so this gives me the current node built as the proper type, so we can reference previous and next. And then this is the creation of new node being inserted. I see. Okay. Okay, so let's do this again then. Because this one was kind of complex. We'll go all the way back, all the way back. All right, so we have our constructor. First, we do our type, which is node t is equal to value, which is a number, no value, which is t, next, which is optional, which is going to be node t, and our previous, which is also optional, also node t. Okay. Then we have public length, private head, which is going to be node t, and we have a private tail, which is also going to be node t. Okay. And then in our constructor, we're going to start initializing. So we're going to say this dot length is equal to 0, and then this dot head is equal to this dot tail, which is equal to undefined, right? So now we're going to start prepending. So if we are prepending, what do we need to check for? So if we're prepending and there is no node, so it is if no this dot head, then this dot head, we're going to say const node is equal to value item as node t, and then this dot length plus plus for our bookkeeping. And then if there isn't anything, then you say this dot head, which is equal to this dot tail, which is equal to what? Node. And we need to return. Otherwise, if it does exist, what do we say? First, we need to attach, right? Attach and then reassign. Okay, so first we attach. So if we are attaching, so it is node.next is equal to this.head. Hey Z-Man, how you doing? Welcome to the stream. And then it's going to be this.head.previous is equal to node, and then this.head is equal to node, right? And so what is this doing? This is saying that our current head, the current node, its previous should point to the node that we are creating. And then once we do that, we say that the head points to the node that we've created. Cool. And I think that should be proper without giving us... You can't be in a code war. What language, bro? No, I'm no longer doing code wars. I'm doing I'm doing DSA. This is data structures and algorithms, the front-end master's course in TypeScript. So this is actually not Java. But I did my code wars in Java at the very beginning of the stream. So if we are inserting at, first we need to do a couple of checks. So we're going to say if the index is greater than this.length, we need to throw an error. So we'll throw new error, say, oh no, right? Then we have another one. So it's else if. What are we else ifing? Index is what? If the index is what? Because there was one that was also index is equal to 0, right? Are you self-taught or degree? I am self-taught. I am teaching myself right now how to implement a quicksort algorithm. So what are we inserting at? What were the 3 issues with inserting? So if it was inserting at the very beginning, then we just do the regular stuff, right? Which is this dot head is equal to this dot prepend, and this is going to return, right? And this was this dot length. So if it was this dot length, then what are we doing? We are this dot appending, right? And we're going to also return. There we go. Now that that's taken care of, what do we need to do? We need to start traversing our stuff. How long have you been coding? What programming languages do you know? I've been coding for a couple of years. I code in Python, JavaScript. I'm teaching myself Java. That's why I am currently working in TypeScript. Cool. So first, what we need to do, we need to say let current is equal to this dot head, right? And we need to traverse. So for let I is equal to 0, I is less than index, and then plus plus I, according to him. What do? We say current is equal to current dot next. Okay, and we have an error with our current. It's possibly undefined. It's possibly undefined. Why is it possibly undefined? No T or undefined, right? Yeah, okay. So now that we've traversed, let's just say this. We're going to say current is equal to current as node T. This is us creating the, and then we're going to say const node is equal to value item as node T, right? You got any apps or websites? Would work at Yahoo? I'm reading your code. You're really good. Thank you very much. I really appreciate that. But I'm mainly right now recreating the code that is the Primeagen's original code. But you can definitely check all of my projects on my socials. If you go to my website, my portfolio right there at the end, you can view all of my websites or all of my work, or you can actually go to my GitHub as well, and you can check all of my work there. All right. So now that we have created our current and we have created our node, we need to start reassigning. So it's going to be this dot head is equal to, no, we can't say this dot head yet. First, it is current dot what do? We are currently on the node and we need to attach to it. So we need to say that current dot previous, first we're attaching. Yeah, so current dot previous is equal to node, right? When you say the one before it is also equal to node. Oh, that's at the end. So once we've attached, so we point the previous to the node, and then we say node dot next is equal to this dot head, right? And then this dot head is equal to node. And then if current dot previous, then what do we need to do? Current dot previous dot next is equal to node, right? And then just return, right? Yeah, because this is it pointing to the node that we are inserting. We are reassigning the node to this, like this dot head to the node that we are inserting, the next to the old node, and the old node is pointing back to the previous. Okay, let's see.
What we did there?
Oh,
It's a little
current dot previous dot next. What did he say? Ooh. Is equal to current, not node. Node dot next is equal to current. And node dot previous is equal to current dot previous. So this has to go down. Node dot next is equal to current, and then node dot previous is equal to current dot previous. Node dot previous is node dot previous is equal to current dot previous. What does that do? Okay, it's just taking the tail from the current and pointing it the same direction. I see. Node dot next is equal to current. Ah, I see how that works. Okay. And then current dot previous is equal to node. Did I add this to my Enki? No, I did not. We'll say implement a doubly linked list algorithm. And we'll say undo all of this. And we will yank this and just paste this. Oh, undo, undo. Shift V, right? And it's going to be yank, oh, yank plus this, undo. What is happening? There we go. Took a moment. All right, let's keep going. Something's happening. Current.previous is equal to node. Okay. Are you a recruiter? Yeah. What's your story, Z-Man? Current.next. Okay, doesn't like this. What does it not like about my traversing? What does it not like about my traversing? Where is your loop? I is equal to 0. Current. Oh, I see. It's current and... Okay. That's fine. Cool. All right. Perfect. Whew! No, I'm not, but my friend who works at Yahoo is looking for full stack developers. I'll contact Bro on his Discord about it. I appreciate that, Z-Man. I really... Welcome to the stream. That is really helpful. I am currently looking for new opportunities as well. And my resume is directly on my portfolio. But yeah.
Now we need to update the tail to point to our newly added node.
Let's keep going.
Tail equals node. Everything's good? There's a lot of links here, people. A lot of...
This is complicated. Trying to get this all down is hurting my head.
This is kind of an interesting one that Java did. I don't really love this one, but it's kind of a fun one in the sense that we have an item T in which we need to find first in the linked list, then we need to remove it. So you'll see that this is available. A lot of times when you're using a list operation, you may not realize how bad this performance could be. My guess is that Java's really, really smart, and they do something like also include a hash map as well underneath the hood. So when you look it up by item, it can instantly look up where this node is and then delete it out. To me, that seems to make most sense, but we'll see what happens here. All right. Maybe. Maybe not. Actually, now that I think about it, maybe not. All right, so what was I doing? Oh, yeah. So we need to do the same thing as a get or a remove at or an insert at. We need to do the whole let current equals this dot head for let I equals 0. I has to be less than.
So this is our removal.
We don't have to do that at all. This dot length. Nice. And, of course, we need to check for current being something. We're going to keep on scrolling until we get to the end, or current does not exist. But I guess you don't really technically have to do that, but for the case of TypeScript, we have to do it, because if I is less than length, current better be a real object, or we've completely screwed up our implementation, but again, TypeScript doesn't really like it. Next, right? So if current does not, let's see, current.value does not equal item, or I guess it'd be the other way around, right? If it does equal the item, we have found it, right? Yay, we're good. So we can break out of here. I guess we could put something in here, huh? We could do it like a current value and a current value, blah, 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 blah. We'll just keep it like this. Very easy to read. Awesome. So current value equals item. We break. Else we're going to keep on scrolling current until we go to the end of the list. If there is no current, there is no item to remove. Right?
True.
That makes sense. So we're done. We're out of here. But if there is one, well, now we have to actually do something about it. So how do we do it? Well, since we're not involving ourselves in this circular list item, what we really need to do is think about the 3 possible conditions, right? Really, there's only one condition. We're just going to have to do some if guards around it. There is the node we want to remove.
Right.
And possibilities of being pointed to, right? So we're going to need to take whatever this is that's pointing and point over. We're going to need to take this one, whatever it is, whether it's undefined or not. If it does exist, we're going to want to point through. Then at that point, we can break these links, and we got it. So this is really just deletion in the most general sense.
Yeah.
So we can do that. So we'll go like this. Or we already have current, which is the thing we're going to want to delete. We can now go like this. Let's go this dot length minus minus. do some bookkeeping. Awesome. We can
Sure.
do kind of a shortcut if we really wanted to. If length equals 0, then this dot head equals this dot tail equals undefined. Awesome. Return. Nothing left to do. We're good to go.
Yeah.
This is great. Still, a lot of if conditions are about to happen, so let's just have some fun and do it.
Conditionals.
Breaking it up a little bit differently. So now that we have this, let's just do that general case. First, let's see if the thing's previous. If we have a previous, let's set our previous to our next. If we have a previous, we need to set it to our next, right? We need to
Yeah.
hop over. That's this top branch right here. Whoop. So if current dot previous, then current dot previous equals current dot next.
Yeah.
That makes sense, right? And again, the other direction. If current dot next, then current dot next needs to equal current dot previous. So
Yeah.
now we've officially removed our current from our linked list. If we started our head now, we would not run into current unless our current is currently our head, right? We need to do a little bit of extra updating at the very, very end here. So now we're going to take our current dot previous equals our current dot next equals undefined. Now we have broken current from the linked list. So now we should theoretically have two separate lists going on right here. Current, which is all by itself, and the rest of our linked list. So we can do a couple extra checks. If current equals this dot head.
Where's
well,
current coming from? Did
that's
he
done,
already
right?
define that?
The hop break.
Oh yeah, he's just
Well,
yeah, this dot head.
so we're done.
This dot head, and then he traversed. Okay.
Current dot previous. We need to walk it back one step just to make sure our tail or our head are now pointing at the newest item. And then lastly, completely break it all off. You don't have to do this in the JavaScript. It's good. Or if current dot this dot
I
tail,
skipped too far forward.
exact same thing except for the other way around. This dot tail equals current dot previous. We need to walk it back one step just to make sure our tail or our head are now pointing at the newest item. And then lastly, completely break it all off. You don't have to do this in the JavaScript land. JavaScript will automatically clean this up for you. And then finally, current dot value. Awesome. I think I did goof up one return right here. Yes. So const out equals this dot head dot value.
If this dot length is equal to 0, const out is equal to this dot head dot value, which is optional, and this dot head is equal to this dot tail, which is equal to this dot undefined, and then return out. Then it's just undefined. So my story is I majored in physics and mathematics, and I graduated in 2014. Both majors opened to many doors in engineering, IT, comp hardware and software, science, tons of careers. I worked at Rockstar Games and ID Software as a physics programmer. I would like to work with you, bro. I know I'm random, but I feel like we can build something together. Of course, I would absolutely love to get in contact and see what we can do together. I mean, I have 2 engineering degrees myself. If you would like to reach out, you can do so through my website. You can just reach out my email, or you can just slide into my DMs here on Twitch, and we can start talking. And we can set something up for sure. I don't mind. All right, let's keep going though.
There you go. There's that one that we goofed up. Did we goof up any other ones? Ah, yes. There's that as well, right? Because we're supposed to return out the value. So
Right.
we're kind of chugging away at this point. We've gotten pretty far out, and now you can pretty much imagine that we have made it to the the last and final parts. It's feeling so close. We're really happy that we're almost done with this linked list, but there's a couple more loops we got to do.
Oh my goodness.
So instead of just doing this, we could probably generalize this, don't you think? Don't you think that we don't need to keep doing this over and over again? Martin Fowler's rule of 3 is usually what I deal with. Since we have one here and we have one wherever insert is, here's insert. We have one right here. That means we can probably do something a bit smarter, don't you think? So let's just take all of this out and use the old rule of 3. I like the rule of 3. It just makes me feel happy when I do it. All right, so do this thing. Oh, we can't quite do it here. This one is kind of unique. Now that I think about it, we can't actually do it here. I thought we could do it here. It's actually here that we can do it. So we'll just pull it out either way. Private get get at, and so this will be an index number. Awesome, and we can go const node equals this dot get at index. If node does not exist, return undefined. Actually, we don't even need to do that, huh? We can just go return node. Oh my goodness. TypeScript. There we go. That's beautiful, huh? We can do value, and really we don't even need to do that. We can actually just There we go. Beautiful, right? We have this nice thing nicely done. Put it down, and then we can go back to our insert and just take that out as well. Might as well, right? Const cur equals this dot get at index, and if this should always work. So we can just take this last little bit right here, right? That's what we're doing right there. Because we already know, of course, we've already done all of our own personal bounds checking. We already know everything's good, so we can just rip it right out. Do that. Awesome, awesome, awesome. We have now achieved full-on, we will achieve at least full-on rule of 3. So here we go, remove at, exact same thing. We need to remove this thing at a specific index. So let's go like this, const node equals this dot get at index. If not node, return undefined, right? There's nothing left to do. We've already found the node, or there's no node to be found. We don't need to return anything. But again, this is where that inner software engineer in me, like, I can't even do it. Even though it's not a rule of 3, it's only a rule of 2. I feel like this removal logic is just so awful, I'd rather kind of abstract it out. I don't know what it is inside of me. This probably happens to you too, where it's just like you can't even handle the fact that that exists. That's at least how I feel. So we'll have remove node, node, t, awesome. We know this thing exists. It's going to return a t, fantastic. And ooh, this one's trying to claim that it's not going to return a t. We'll just go like this, why not? There we go. And now we just need the current needs to be replaced as current node. Awesome. So there we go. We've just generalized this function really quickly, pulled it all out. I wasn't actually technically planning on doing this, but it just feels right to do it. I can't actually not do it. Sometimes it's how I feel. So there we go. We now have this removal of the node, which means that our remove at and our remove can now share the code. Return this dot remove node current. Very great. And then, of course, remove at. We can do that as well. Awesome. So we pretty much have everything written except for one last little bit, which is our get function, which I deleted and didn't keep. So we'll just write it really quickly. Current equals this dot head for let I equals 0. If you guys were smarter than me and you actually kept it around, good on you. I didn't do that. This dot length.
The slot length should be index. Okay.
I struggle sometimes. Current equals current dot max. There we go. Return current.
So, when you get hired at one of those AAA studios, man, it is tiring. But ChatGPT or drag and drop software for programmers will never be automated if that's what's on your mind. I'm not concerned about ChatGPT at all as a programmer. I think my job is safe and sound as someone who is familiar with programming. I would love to build a program that has machine learning capabilities or AI. But I think it could be overly exaggerated how much it is going to replace a software programmer. And Ofu, you're saying if you wonder if plain JavaScript can implement nodes. I wonder if that can do that too. Because technically these are all like, this is TypeScript specific. I don't know. I don't think so.
There we go. So we've actually gone through and we've implemented every
Maybe.
last detail
You
when
can-
it comes to this linked list. So
You
I
can do
know that
linked
was a
lists
lot.
in JavaScript,
I see faces of, oh my goodness, why
on
would
lead
you do this
code.
to us? I'm sorry, I didn't, this is why.
But let's see what it says. Get here. Let current is equal to this dot head, and then it's traversing. And then we're going, okay.
I tend to want to skip this section because it's just so big. It's hard to see why it's like so complicated, but it's really not complicated at the same time as it is super complicated. And I think this really goes to show you that if you have the wrong function interface, it can make things a lot more complicated.
Okay. Let's start doing this again. So we are going to append. And appending does what? It adds to the end. Remove removes from the end. Get, and then remove at. Okay, so he did the get at, but then get and get at. So it's going to be a get at, and it's going to be index, which is a number. And it's going to return t or undefined, right? And is that what he said? But anyways, let's go back to the append. What are we doing? First, we need to append. And if we're appending, we need to check for something. if no this dot head, return head is equal to this dot tail, which is equal to node, right? So const node is equal to value item as node t. Doesn't like node t. Am I unable to access? What did you expect? Has a type of any. Oh, okay. Well, let's go back and redo the append.
So it's all about if current equals. We're going to need to take this one, whatever it is, whether it's undefined or not. If it does equal the item.
Wait. Prepend. Append. What is he doing here?
Actually, now that I think about it.
Okay.
All right, so what was I doing? Oh, yeah. So we need to do the same thing.
I see. So append was fairly quick to get done, right? So it's just.
Move it. Is that
what is happening? Why is my thing not going back?
This is kind of all right. So this is kind of an interesting one that Java did.
Oh. Whoops. Because append was from the other one. Okay. So if no this dot head, return undefined. Right? Because if there isn't anything, you can't remove. And so what happens if there is? He's introducing a remove add at the end. Yeah. So if there is, what we need to do is we need to overwrite it. So it's going to be current dot next. Current is equal to current as node t. Right? So oh yeah, we have to traverse. Oh, traverse first. So current is equal to this dot head, and then for let I is equal to 0, where's index? This is where I see he does the remove at. Oh, it's gonna be this dot remove at, and it's gonna be item. T is not assignable to type number. What happened to all of this? What happened to my append?
So we do have time. Would be all right.
Let's stop here for a moment and figure out what the fuck happened.
Bookkeeping. Attach it. This dot head. First item to do something. Put it.
Without thinking, I'm just going to copy it down for the sake of keeping what's happening with this dot length. Plus plus const node is equal to value item, right? As node t. And then we need to if no this dot tail, which is equal to undefined, and then return
Into this list. All right. So this is kind of an interesting one. So next.
and then if it does exist, this dot node dot previous is equal to this dot tail. This dot tail dot next is equal to node, and I think we have to just return.
Out of node. This dot tail equals node.
appending, so we're moving the other way. Removing if this doesn't exist. Let current is equal to this dot head. No. And then he goes into all of that
Alright,
weird bullshit that I
Alright.
don't like.
Maybe not. Actually, now that I
The
think
thing
about
is
it.
him
Maybe not.
jumping all the
Alright,
way
so
SQL and C# web dev.
what was I doing?
Well,
Alright,
that's not
so we
bad.
need to do the same thing as
Yeah. So current is equal to this dot head. And then 4. I see. Let I is equal to 0. Current and I is less than this dot length. Plus I. And what were we doing? We're removing here. So do I need to take away from the length first? Current is equal to current dot next. Okay. And so if I'm removing, it's going to be this dot length minus minus. And it's the same thing. Const node is equal to value item as node t. What do you not like here? Undefined is not assignable as node t. Well, it's not. No. I don't need the... This is where we will be returning the value. So if we're removing, we're going to say... We are on the node. The next node has to point to the node before, and the node before has to point to the node after, right? So current dot next is equal to current dot previous. Node dot previous. Or is it this dot previous?
or current does not, because no current. There is no item.
Oh, I have them backwards. So if it's this, we move down afterwards. And that got rid of my error too. I see. They got rid of my error, and it said here if current dot value is equal to item break. If there isn't a head, return undefined. This dot length minus minus. We're not returning. We'll just return, baby. Okay.
Item to remove. Is what we really need to do is think of cards or pop.
Yeah. So then we do the all of the other stuff.
General case. First,
right. If this dot length is equal to 0, because we can't remove anything, then what do? This dot length is equal to, or this dot head is equal to this dot tail, which is equal to 0, and then we need to return. Current dot head is equal to current dot tail. What do you not like? Number is not assignable to type node T. Okay. A number is not assignable to node T. Undefined. And then return, right?
let's see if over. That's the so if current.next, our current is currently our head, right? We need to do a little bit of extra updating at the very, very end here.
Oh.
And again, so
Yeah, it's equal to undefined. Cool. And then if current dot previous, and then it says current dot next is equal to current dot previous. Right? And the same thing is that if current dot next, then we need to do the same thing, which is current dot previous is equal to current dot next. And what do you not like here? Is possibly undefined. Okay.
Current dot next equals our current dot next equals undefined. Now we have broken current from the
Right. Current dot previous, which is equal to undefined, since we are removing it. But it still doesn't like something somewhere.
linked list. So now we should theoretically have two equals this dot head. Well, then that's bad, right? So we can't quite break that, can we? No, we can't. See, operations become very obvious right away that you've done something wrong in the list. And then
this dot head is equal to current dot next.
Or if current dot this dot tail, exact same thing except for the other way around.
Okay, so there's a bunch of ifs that we need to still do. Wow, if current is equal to this dot head, this dot head is equal to current dot next, and then it's the same thing. Is equal to this dot tail. This dot tail is equal to current dot previous. Okay.
This dot tail equals current dot previous. We need this item. So.
And we need to return the value. Okay, so then we need to get index. So they're doing this is where he does the
return.
Yeah, see, like I don't really like this course because it's all very goofy. If this dot length is equal to 0, we need to do const out is equal to this dot head, which is dot value. Okay, and then return out.
Yes.
If no current, return undefined. Yeah, that's what I thought. And we need to take this. Okay, yeah. This dot length minus minus, since I am not taking care of my bookkeeping. Return undefined, since this is what I needed. Current is equal to current dot next. Return out. Return current dot value.
There's that as well, right? Because we're supposed to return out the value. So we're kind of chugging away at this point. We've gotten pretty far out, and now you can pretty much imagine that we have made it to the the last and final parts. It's feeling so close. We're really happy that we're almost done with this linked
previous
list. But there's a couple more loops we got to do. So instead of
just
doing this,
next, which is equal to undefined,
we could generalize this, don't you think? Don't you think that we don't need to keep doing this over and over again? Martin Fowler's rule of 3 is usually what.
One more time. So when we are removing, there's a few things that we need to take care of. We need to traverse first. Then we're traversing first before checking if there is no head. We're traversing first before we check if there's a head. This is in the remove. Okay. And then if there isn't anything, we return an undefined. If there isn't anything and we return undefined, and that's false, then we take away from the length of the full list. Okay, so we take away from the length of the full list, and then we need to do a couple of checks. If this list is now 0, then there was only one node, and we return that. which may or may not have a value. If there was a previous, then we need to overwrite if the current is the head. Then this dot tail needs to be the previous. And if it was the tail, then this dot tail needs to be the next. Current dot previous, I think. And this is this dot next, right? I think these are backwards. Let's double check here.
Would I do something a bit? The rule of three, it just makes me feel happy. Quite do it here. This one is kind of unique.
No, we're back at the get here. Let's double check here. If current is equal to this dot tail is equal to current dot previous. No, that makes sense. If current is equal to this dot tail, so we are at the tail. I see, because of the way that it's pointing. So it goes, we point this way, then we need to point back to the previous node, which says this dot tail is equal to this dot previous. I see. Previous and next. Okay. Now we're going to go back and do this again.
All of this out is kind of at, and so constant node equals this dot get at index. If node does not exist, return undefined. Actually, we don't even need to do that, huh? We can just go return node. Oh my goodness. TypeScript. There we go. That's beautiful, huh? We can do value, and really we don't even need to do that. We can actually just, there we go. Beautiful.
Okay. So we're going to build this new function then. After remove at, we're going to say get at, and it's going to be an index with a number coming in. And what are we going to return? T or undefined. And then in here, we're going to say this dot return this dot get at index question mark dot value. Okay. And then what's in here? This is where we would traverse, right? So this is let current equals this dot head, right? For let I is equal to 0, I is less than index, I plus plus, or plus plus I. And this is where we would have our thing. Its current is equal to current dot next. And then what do we need to return? Current. Now, what do you not like? Object is possibly undefined. Index cannot find name index. How? Oh. What do you not like here? Oh. This is node T. So then it's like if no current, if no this dot head, return undefined. And this should take care of that, right?
Right? We have this nice thing, and equals this dot get at, right? Const cur equals this dot get at index, and if this should always work. So we can just take this last little bit right here, right? That's what we're doing right there. Because we already know, of course, we've already done all of our own personal bounds checking. We already know everything's good. Now take if
Where did he build this?
insert thing. Nicely done.
He didn't.
Right there.
He didn't. So he replaces all of his code before even
This-
building it.
We've already found.
He doesn't even build the app.
Or there's no
The
just from what it is inside of me. Do it, even though it's not a rule of three. So T, fantastic. I wasn't actually. I feel share the code. And then of course remove
where's
node, current. Very great. And then of course remove at. We can do that as well. Awesome. Deleted and head for let on you equals current dot. We've implemented every last.
Okay. I see. There we go. So if current on this, return that. And then since we have this here, we can then get rid of... So this is going to be... Let current is equal to this dot get... Oh, remove at. So we'll go up here. Where's the append? So traversing is up here. This dot get at index idx dot value. No, as no t. As no t. And then we don't need to do this. And we don't need to do this. Right? Is that what you just said? Okay. So we successfully replaced one. And then we'll do the remove node. I'm all out of brain juice at this point, because he has jumped so far all over the place. And we'll get the remove node. Remove at. Oh, he's putting a helper function for his helper function. Okay. This dot get at index. Okay. Const node is equal to this. And if no node, return undefined. Right.
Awesome.
And then he's doing another one here. Private remove at. Private remove. No. Remove node. Okay. And what are we getting? Node as node t. And what is it returning? Nothing. Void. Right? Is it returning void? Well, anyways.
We know this thing exists. It's going to return a t.
Yeah, not void, but t. So this is going to be returning t. This is going to take away from the length. So this dot length minus minus. So if we're taking away from the length, so we're just going to say, yeah, so it's going to do this line here. So 38 up. 10 up. It will be this. And we're going to go down and we're just going to paste. and or undefined. And what is he replacing?
Fantastic. And, ooh, this one's trying to claim that it's not going to return a T. We'll just go like this. Why not? There we go. And now we just need the current needs to be replaced as... There we go. And now we just need the current needs to be replaced as...
Oh, so he pulled all the way down to current.value here. Return undefined, current.previous, current.next. Current.previous, current.next. Oh, he did the whole thing. All right. So I took the whole thing out, pasted it in here, and then said for this whole thing. He ended up replacing something. So he did this, and he said S, and then he said node. What is happening? Undo. So this, and then he said this S. Jesus. / current with node. Oh, for every line, right? For every line, current for the selection, right? Why didn't it do it for everything? I see. Current with node. And I need to figure out what node is then.
current node. Awesome. So there we go. We've just generalized this function really
It didn't replace this. Okay.
quickly, pulled it all out. I wasn't actually technically planning on doing this, but it just feels right to do it. I can't actually not do it.
And then
sometimes
I need to, in my here, I need to call this dot remove at item.
that's how I feel. So there we go. We now return this dot remove node current. Very great. And
Okay. Let's start move node current. But what the
then of course
fuck?
move at, and our remove can
If no current, return undefined. Okay. Okay.
now share the code. Return this dot remove node current. Very great. And then of course remove at. We can do that as well.
And remove at will do that the same thing. Okay. Return this dot remove node, and it's going to be node. Okay. It still did not do. Okay. So all of these highlight, and we are going to change current with node. Why did you not do that the first time? Okay. This is IDX. IDX. And we're going to stop here.
Awesome. So we pretty much have everything written except for one last little bit. which is our get function, which I deleted and didn't keep. So we'll just write it really quickly. Current equals this dot head for let
Friends versus
0.
logs telling me I got
If you guys were
fixed
smarter than
too
me
many
and you actually
bugs.
kept
I
it
got
around,
fixed too many bugs.
good
What
on
does that
you. I
mean?
didn't do that. This dot length length. I struggle sometimes. Current equals current dot next. There we go. Return current. There we go. So we've actually gone through and we've implemented every last detail when it comes to this linked list. So I know that was a lot. I see faces of, oh my goodness, why would you do this to us? I'm sorry.
Yeah.
Equals current. So we point to that one. Node previous equals current previous. Awesome. So we have our two correctly attached ones. So now we need to get the reverse out, right? So that means our current previous, the one that we're used to be pointing to, which was B, I believe, in the example, now needs to point to the node, which also means the current's previous next needs to point to the node. Yeah.
TypeScript,
So
TypeScript is a headache.
as node's previous next needs to be node. Right? I think that's what I had. No, I didn't have it. I had it. You're right. So it should be node previous. Node's previous, which is current previous. That previous is next need to point to the node. That way our two-way linking is correct. So our previous next.
So this is node.
Right? Okay, you're right. Good eye. I can't believe you spotted that one. That's just so astute.
And it's going to be equal to current. Okay.
Are you using Vim here?
Using Vim?
Yeah, Vim.
I always use Vim, okay? It's literally my entire online shtick is the fact that I use Vim. And I might be like the second fastest. There's word that George Hotz is faster than me. I don't know, but one day we'll have a competition. Maybe he'll join me and do a 25 algorithm super speed run.
We'll see.
I might have another bug.
Oh gosh.
Are you going to go do that right now?
If you do remove undefined
Axel?
and current is undefined, will everything just blow up?
No. So let's look at that. That's good. That's a good question. So the question was, if we did remove undefined and current's undefined, would we blow up? Well, one, you'd have to be breaking the contract, which you'd have to do TS ignore, which we all know when you do that, you have to go work at Facebook for a year. So nobody wants to go do that, right? Joke. Enjoy the joke. I'm sure there's plenty of people that want to work. My best friends were. My views are my own. Okay, anyways. Second, this right here. It's the value that we're comparing. It's the container node that we're comparing. So it's not.
So I could break it. But I'd have to
No,
break-
it's
I'd
the
have to break
container
all the
node.
contracts.
Even if you did break the contract, what would end up happening is that
I feel like through all of this,
node.
this last
the
little bit,
container's
the
value
6-minute video, is going to be
right?
an error
So
that we have in our code.
value would have to then equal undefined, which means that current does exist, which means that it could be removed.
Sure.
So
But
you
I'd
couldn't
add
have to break
I'd
it.
have to add something with the value of undefined.
Yes, you'd actually have to instantiate this thing. Can you even do that? Can you do const test equals doubly linked list undefined? Is that possible? Besides for the fact that I'm not. Oh. Oh. You can't do that. Oh, really? Did I just. Oh my goodness. What am I doing? There we go. Yeah,
I'm going to have
okay,
to
that makes
compare
sense.
his code with my
Well,
code
that
later
doesn't make
on.
any sense. I don't know why you do that, but yes, you can do that. That doesn't break anything, right? Because it's the value that we're comparing at, right? So since we're not comparing the node, we're comparing the value within the container. So that means it had to be a value provided.
Because there's a
within
lot
the
happening
WS,
here.
which means I should be able to remove it.
And the methods that you have written are mainly for Java based.
I think what I did is I honestly went to Java list and took Oracle helps. Oh my goodness. I took I took a lot of these, not contains all. Get there is remove, so you have like a remove index. We can't overload functions, so I had to like rename them. Remove became remove at, remove object, right? There became this whole thing.
Is there any specific reason you have chosen Java or JavaScript when doing this coding for Doubly linked list?
So the reason why I chose JavaScript over Java, that's the question. And so
the Java or JavaScript, I think you've shown the Java methods, right?
Yeah, I showed the Java methods because Java is a fairly complete language, and it's a pretty easy language to show a lot of computer science kind of topics in, right? It's easy, it's safer, you're not going to segfault yourself, but you will get null pointer exceptions, right? You will get these other things. It's a fairly simple language to kind of make these comparisons in, so I just kind of brought it over. I used TypeScript because it's the most accessible language right now. C is obviously the best because it really just shows you that raw memory is raw memory, and you tell it what it is, and that's what it is, right? And so I didn't do it that way.
I see. All right, well, let's see. We might.
someone is correct. So there is a problem right here. So obviously when we get at 2, something has gone wrong. So we could debug this, which is just going to be a lot of fun. Do we want to do a debugging session? Yep, okay. We'll do a debugging section. So what I'm going to do is I'm actually going to add a fun little print statement right here.
Okay,
debug,
so
it's simply going to go for...
we'll just watch this, but then I will
where are
copy
we?
the code and
Yeah,
learn from that
yeah,
at
jump
a
in
later
here.
date when I
Can I
update my
yoink?
Enki.
Oh, why didn't I yoink you? There we go. We're going to do that. Debug, paste it in. And every time we do this, I'm going to go let out equals this. I'm going to go console dot, or not console log, out plus equals I points to current dot value. Yeah? Isn't this beautiful?
Okay.
Console dot log. Oh man, these are just the worst ones. So the first thing we're going to do is I'm just simply going to print everything and see if I can catch the error just by looking at it. I don't really want to debug these things. Let's see. What's the test? Where did you break at? You broke at line 6. Oh, I knew. All right, so if we do this, we should be able to get this. That means my append function is likely the thing that's incorrect. Append, jump in here. What is it? So we're going to go right to here, and we're going to go this.debug. I know, isn't this great? So let's just see what happens right here, because I'm pretty sure that's where the problem is. Beautiful. So let's see. 0 points to 5, 0, 1.7. Oh, look at that. Look at that. And so that must mean that our get is totally the wrong thing, isn't it?
Someone's saying the private remove.
Huh?
Private remove.
We'll get there, because we're breaking at appending. So I must have something wrong right here, which I do, because I am a dummy, which is I didn't simply just use that. So this should hurdle our first problem right here. There we go. It was our get at.
Did I do that? Yeah.
Oh, I was hoping that it would just work. And I can just be like, that's right. All right, so next problem, remove at. If we remove one, so this must be where this whole bug is right here. So we're going to jump in here. Oh, there's that beautiful list interface. Remove at. So we get this node, which is now the correct node. If it's not this, then we do this. Now people are saying the remove at. Okay, chat might have been correct here. So if it's 0, we remove everything. Perfect. If nodes previous exists, then nodes previous needs to equal nodes next. Okay, that makes sense. We were breaking ourselves off from this list. If nodes next exists, the nodes next.
See? I knew it.
Yeah, see?
Okay, something was off.
Thing, right?
Okay. I wasn't completely there, but I had an idea. So this is also just completely node.next. Undo. What the hell? Oh, that was period. Period is doing what? Replacing and pasting? Oh, is that last action? Undo? No. Huh. Okay. Node.next dot previous. Previous, and then it is node.next dot node.previous dot next. Now what do you not like? It's possibly undefined.
Nodes next, or nodes previous next needs to now jump across to node next. Nodes next previous needs to jump across to node previous. Classic blunder. I practically started a land war in Asia at this point. So there we go. I believe that would be the bug, right? Everyone agree?
No.
First try. I knew it. It was a first try. I knew it. All right, there we go. All right, thank you. Thank you. Wow, the claps are outstanding here. You can't hear them because we're not supposed to clap. So there you go. That is a doubly linked list. They're very, very hard to write, honestly, and it's difficult due to an exercise of like minutia. It's not difficult because the concepts are hard, and so
Oh, it passed.
you should be surprised if you run into a million of these
Oh
problems.
no, it didn't.
I remember at university we had to do a bunch of these, and it's just like every time I implemented something like this, it just always is a headache, right? You're always just like, goodness gracious, like what else is wrong here? We had to implement a trees.
If this dot length is equal to 0, this is equal to head dot value. This dot head dot out. Okay, node dot previous is equal to node dot next dot previous. Okay, if node dot previous dot next is equal to node dot next. If node dot next dot previous is equal to node dot previous. Okay, there we go. I think now it should work, because my thing was backwards. It still failed. T and undefined. Not all call paths return a value. 65. Oh. I forgot my return statement here. Expected this, returned none. Okay, so what I'm going to do is I'm going to have to go through my code outside of this time because I'm losing mental capacity at this point. So we'll finish off this video, we'll
deleting
wrap
from
up the
trees, which
video,
we're not
and
gonna do
then
tomorrow, but if you do deleting
I
from
will
trees, it's
upload.
just the exact same stuff. You need to have the parent pointers, and you do all this pointer updating, and there's just a bunch of cases to it, and we'll go over all the cases. But
So
it's just
doubly
an
linked list,
exercise
he's
in,
saying
like, how well are you at remembering to do next.previous, not just .next.
maybe it's not something where
Awesome.
like it's complicated to learn, so
think
maybe I
that-
should just try and re-implement it time and time and time again.
We remove a node, we toss it away. Have you ever had an instance where you had to keep track of the history of all the nodes that have been removed?
I've never had an instance where I've had like a history. I wouldn't even know quite what to do with the history. It feels like a history of the nodes to be removed would be some sort of wrapping class, right? You could do some sort of higher order, linked list, right? Linked list with history or something like that, as opposed to implementing it directly in a linked list. Yeah, it'd be interesting. I don't know. I can't think of a purpose off the top of my head, but that doesn't mean other than creating an undo, right? I assume that's what it's for, is creating some sort of undo. But that would be, in a sense, pushing your app state to a linked list that you could walk back. Funny enough, whenever you bubble up from an HTML event, it's just using, effectively, in a sense, it's a linked list, because as you traverse your elements and go through that, you're really just walking parent pointers, which really is just like a list, right? And so it can be treated very, very similar. But yeah, that's interesting. Never thought about an undo. I've never had to program an undo. I've always been curious to program an undo. But it's one of those curiosities I don't actually want to do, but you could do it. I don't actually want to do it, because it would just be linked list hell.
1,
right?
2, 3,
really
4,
trying to give
5,
us states
6
and addition and moving
sections
through. And
left.
what happens the moment you change, but you've undone twice, you create a branch in your program, so it's no longer a linked list, it's a general tree. You pretty much invent Git at that point, and if you've invented Git, that's just a bad plan.
All right. So I think this is a good spot to call it for the YouTube video. Well, if you followed this far, thank you so much for following. I know that was a little bit rougher than I would have liked it to be, but doubly linked lists are not easy. So I hope that you learned something here today. And if you did, come back to the next video. We will be covering trees and tree searching. So without further ado, see you guys next time.